Okay, in this video we will talk about AUC and ROC curve, okay, in machine learning. Now if you remember from my previous video, we talked about the basics of the ensemble learning, right? Now when we'll discuss about different ensemble learning algorithms, we will be using this AUC and ROC curve very extensively. So that's why I thought I will be creating this content first, then we will go very deeper into all these different ensemble learning algorithms. Now what is AUC and ROC curve? Now by definition, and ROC curve is basically, the name is like receiver operating characteristic curve. It's a fancy name. We'll see the details about it very soon. Okay, it's basically a graph showing the performance of a classification model at different classification thresholds. Okay, now if you remember from my previous videos, we talked about mean square errors or root mean square errors, different measurement for measuring the performance of a regression model, right? Now AUC and ROC curve, you can say like it's a measurement of the performance of classification model. So for different kind of classification model, we can basically generate this curve to determine whether our model is actually performing well or not. Okay, so this is a very sophisticated method and used very extensively as well nowadays. So it is really important we understand this one. Okay, so by definition it looks like ROC is a curve. Okay, and the curve, what it plots, basically it plots two things. In the x-axis it plots the false positive rate, and in the y-axis it plots the true positive rate. Okay, and by definition AUC stands for the area under the ROC curve. Okay, so basically AUC is a number, it's a measurement, right? So it's a measure, it basically measures the entire two-dimensional area underneath that entire ROC curve. Okay, now AUC provides an aggregate measure of performance across all possible classification thresholds as well. Okay, we will understand very thoroughly why AUC is needed. Okay, and if you see it over here, there are certain terms coming up over here. It's called classification threshold, right? And we have over here true positive rate, and we have over here false positive rate, right? So first we will try to understand these concepts, then slowly we'll move to AUC. Okay, so to understand this stuff, first we need to understand the confusion matrix. Okay, now for that what we'll do is today we'll be using a very simple data set for an example. Okay, so this is the wine data set. Now we will be working, when we'll be working with different ensemble algorithms, we'll be using this particular data set extensively over there. So I just took couple of features from there and just created this particular table over here. Now if you see it over here, a particular wine, whether it is good or not, based on, we basically determine based on its quality. If you see, it's a number over here, right? Now if we just convert this quality into good or bad by, let's say if the wine quality is greater than 6 or greater than equals to 5, we'll keep it as good, otherwise we'll say it is bad wine. Okay, now the quality of a wine depends on a lot of factors like pH, the alcohol content of it, the density of it, some other factors as well. When we will see the actual data set, there are I think 8 to 9 different features we'll be working with. Now to just demonstrate what do we mean by ROC curve and AUC, it should be sufficient, this particular example. Okay, so we have this data set. Now we'll move to confusion matrix first, because we need to thoroughly understand what it is. Now what is a confusion matrix? Now basically confusion matrix is a performance measurement of a machine learning classifier where output can be 2 or more classes. Okay, so here we will see an example of a classifier which deals with 2 classes. Now the same concept can be extended to accommodate the classifier which is actually classifying more than 2 classes as well. Okay, now we will basically, whenever we talk about confusion matrix, we basically create this kind of matrix over here. Okay, now over here if you see, like we are dealing with the wine data, right? Now this things means like in this way, in these places we are actually showing up the predicted values over here, okay, through this axis, and through this way we are actually showing up the actual values over here. Now here basically what this particular box means, here we basically predicted true or good wine, right, and actually the wine is also good over here, okay. Now in this box, whatever we are showing up, we predicted the wine is good, but in reality the wine is actually not good over there, similar way, okay. Now based on this one, like our predicted values and what is the actual value, the actual output, there are 4 different concepts or 4 different terms we need to know. One is true positive, another is false positive, another is false negative, another is true negative over here, okay. Now what do you mean by true positive? True positive means we predicted that something is good, that means the wine is good, or a particular customer has some terminal illness or not, okay. We predicted something and it is actually true, that means when he tasted the wine is actually good, okay. So this is called a true positive scenario, right? So we predicted the actual output and that actual output is true over here, okay. So these 2 terms we need to distinguish, because here you are doing the actual prediction, whether it's a positive or negative, whether it's a good or bad, something like that, okay? Whether a particular person is having terminal illness or not, those stuff, right? And the true means like in reality we are seeing whether that particular thing is correct or not, okay. So we saw true positive. Now what is true negative? True negative means we predicted negative, right? So we predicted something negative or bad, that means we predicted the wine is bad, okay. This is the case over here, okay. And also it is actually bad as well, that means we predicted correctly over there, right? It's actually true, the wine is actually bad over here, okay. So this is called true negative. Now what is false positive? False positive means we predicted that the wine is good, but in reality the wine is actually the bad one, okay. So this is called false positive over there. And what do you mean by false negative? False negative means this case over here, right? So we predicted that something is bad or negative, okay, but in reality it is actually good. So this is the false negative case over here. So there are 4 cases are arriving over here. Now based on these 4 cases we can build up. We'll be slowly moving to the ROC and AUC over there, okay. So we'll try to remember this particular slide, then we'll move to the next slide, and there are certain terms we need to understand before we plot the ROC curve. The first term is the recall or sensitivity, okay. Now what do we mean by recall and sensitivity? So for that what I'll do is I have just copied the last 2 columns from our data set, like what is the actual category and what category we have predicted through our machine learning classifier, okay. So now when we talk about recall or sensitivity means like a particular model, how much sensitive it is to the data, right? When it is basically picking up the good examples or positive examples, how it is classifying those positive examples. So when we talk about sensitivity, we always look for all the positive data points, okay, and how we have classified them. So over here if you can see there were 4 actually good wines over there, right? Now how we have predicted them? The first one we predicted correctly, the second one also we have predicted correctly, but the third and the fourth one we did not predict it correctly through our model, right? So now if we just write which one is what, if you just remember this previous slide we have seen, so this is the true positive case, right? We have predicted something is good and it is actually good, right? Second one also is the true positive case, right? But the third one is we predicted something is negative but it is actually good, right? So it is a false negative one, right? Similarly the last one is also the false negative case, right? So sensitivity or recall is defined in this way. So we have our true positive case and all the true positive and the false negative case over here as the denominator over there, right? So in this case basically we are having total two positive case, and with 2 positive and false negative case we are having total 4 numbers, right? So this is our recall value over here. Now let us just step back and think about it. What does intuitively this one mean, right? Now if you see, this one is actually meaning how we are classifying the good things, the positive things. Let's say we are talking about a classifier which is actually classifying two classes over here, right? Either a good wine or a bad wine, right? So now by this particular measurement, we can easily see how we are measuring the good part of it, right? Whether we are correctly measuring the good part of it or not. So if you think about this one, if our model sensitivity will increase, we will be basically classifying the good examples in better way, right? So the more sensitive it will be, the more good examples will be classifying as good only, right? So, and now if you see it over here, this particular measurement it will be always less than equals to 1, right? So maximum value it can have 1 when we will all classify all these good examples correctly over there, 100%, right? So as I said, so this metric corresponds to the proportion of the positive data points that are correctly considered as positive, right? With respect to all the positive data points we have it over here. In other words, the higher the recall or sensitivity value, the fewer positive data points will miss over here, right? So basically the proportion of the positive data points that are correctly considered as the positive over here, right? So that's the main message behind this particular line. Now this particular measurement is actually called true positive rate. So if you remember the first slide, so this was our y-axis over here, right? So we successfully defined the y-axis of our ROC curve, right? Now let's move on. Let's talk about specificity. Now this is another measurement. Now in previous slide when we talked about recall, we talked about all the how we have seen like how we are classifying our positive examples or positive data points, right? Now in specificity, we are actually talking about the negative data points. That's the difference over here, how we are classifying the negative data points over here, okay? Now if you see in our case, the first example we have correctly classified is as bad. The second example we missed that. The third example we again correctly classified as bad, right? So if in similar way, if I just write it down in terms of our confusion matrix values, right? So here we actually predicted bad, which is actually bad, right? That means we predicted negative, which is actually true. So that means true negative over here, right? Now this one is false positive because we predicted something is positive, but which is actually bad, right? So it is a false positive. And the last one is again the true negative case over here. So in similar way, if we just define the specificity over here, so it will be all our true negatives divided by true negatives plus our false positive over here, right? So how we are classifying our negative examples over here, negative data points over here. Okay, now if I just talk about in terms of number of data over here, so our total number of TNs are 2 and TN plus FP is 3, so that will be the value of our specificity, right? And again it will be get less than equals to 1 over here, right? So now if you see it over here, if all our data points we are correctly classify as bad, like all bad we are correctly classifying it, so this will become 1 over here. That will be the ideal scenario, right? So as we have seen, like this matrix corresponds to the proportion of the negative data points that are correctly considered as negative. Okay, so that's all this particular metric is talking about over here. Okay, now so in other words, this is the higher the specificity, the fewer negative data points we will miss over here. Okay, now this is called true negative rate, TNR. Okay, so now think about this one. Now we have in our numerator we have taken the true negative values, right? That means the actually which were correctly classifying it as negative, right? Now instead of this one, if we just take false positive and as our denominator, this will happen when we will we will just take 1 minus specificity, right? So this will become our next one, which we'll talk about very soon. Okay, now that one make more sense. So if I just go to the next slide now, it's called fallout. Okay, so the fundamental wise it is same as specificity. We are looking into the bad data points and how we are classifying them. Okay, and similar way we have defined the TN and FP as well. The fallout defined as FP as our numerator over here. Okay, and the same TN plus FP as our denominator over here. Now if I just think about this one, this is 1 by 3, right? Because we have 1 FP and TN plus FP is 3 over here. Now this particular measurement looks better because think about this one. Here basically you are raising a false alarm over here, right? Because you're predicting something good but which is actually bad over here. Okay, so this measurement is actually nothing but 1 minus specificity, right? Because specificity is TN divided by TN plus FP. If I just do 1 minus specificity, we will get this particular value over here. Okay, so now this is also has to be less than equals to 1. Now what this particular matrix corresponds to? This particular matrix corresponds to the negative data points that are mistakenly considered as positive. Okay, so that means the higher the appear, okay, so this is called fallout or appear, the more negative data points we will be classifying over here, right? So we will not do really good in terms of the other class, that means the negative class classification, when my fallout rate is very high over here. Okay, so this is called false positive rate. Okay, now this actually is our x-axis of our ROC curve. Now let's move on. Let's see the data set again over here. Okay, now if you remember from the first slide, we have defined the true positive rate and the false positive rate over here, right? Now we still not define, there was another term over here, if you remember, it's called the threshold over here, right? So in the definition of the ROC curve, we have seen it's a curve of true positive rate and the false positive rate based on the different threshold level of its feature, right? So now that one we will try to understand now. So for that, what we'll do is we will take a particular feature over here. Let's say alcohol content. Okay. Now, if you see it from this data set, we can see like whenever we have our alcohol percentage is greater than equals to 9.5, we are seeing like the wine quality is actually good. So if I just mark those records over here, this one and this one over here, right? We are seeing the actual category is good over here. Okay. Now, if you see, there are certain other good quality wine as well where the alcohol percentage is less than equals to 9.5, right? But based on some other factors, maybe it is good over there. But at least we can see if the alcohol percentage is greater than 9.5, we are dealing with the good wines over here. Okay, so now we can what we can do is we can set up a threshold for our classifier over here. Let's say we can write something like this one. If my alcohol percentage is greater than equals to 9.5, we will predict that particular wine is good over here. Okay, now here we are taking an example of a single feature. Okay, the same stuff we need to do for multiple features as well. Okay, now think about this one. If we just relax that particular threshold a bit, let's say we are setting up a new threshold called 9.1 over here to get this particular good wine. Because if you see the two things we have discussed over there, the sensitivity as well as the specificity, right? Now sensitivity deals with how many good examples we are classifying as good. That means our main motto is we need to classify as much as good possible, right? So we cannot by setting up this 9.5 threshold, we was actually omitting this particular good example over here. Okay, that's why we are thinking of now downsizing or basically relaxing that particular threshold to 9.1 to accommodate this guy over here. Now think about, now see this one, when we set up this guy as a threshold, right? Now we are including some bad examples as well over here. If you see this guy, because here also alcohol percentage is greater than 9.4, right? Here also, if you see, the alcohol percentage is greater than 9.1 over here, right? So here also it is greater than 9.1. Even here also it is greater than 9.1. So if you see it over here from this particular exercise, when we relaxed that threshold limit a bit to accommodate the good examples, we actually accommodated not only the good examples, some bad examples as well over here. Okay. So this is always will be the case when we talk about a classifier, right? To accommodate more good examples, when we relax the threshold or change the threshold, there will be always a chance we will accommodate the bad examples as well over here. That's why the optimal decision making is needed over here, right? So let's try to draw a diagram over here, okay, to understand this one a bit. So for this one, what I did is I just draw this breakdown diagram over here. Okay, so here if you see, if we just set our threshold limit to greater than equals 9.5, we are basically talking about this point over here, right? And when we talked about threshold limit as greater than equals to greater than 9.1, we are basically talking about this particular threshold over here, right? So this is initially when we did that one, this is our threshold limit, right? So we are only getting the good wines over here, right? Now if you think about this one, if we set our threshold to somewhere over here, okay, over here if you see, if I just talk about, these are the whole number of wines, good wines we have, the number of wines, right? Here we are so much picky over here, right? So that means we are only picking up the good wines, but we did not collect all the wines over here, good wines over here. Suppose I have a bag of good wines and bad wines bottles, okay, and my classifier wants to classify which one is good wine and which one is bad wine. So if I just make my threshold limit very high based on the experiences or the data we have seen it over here, it's possible that we will only pick up the good wines, but the thing is that we will not pick up all the good wines over here, right? Now to pick up all the good wines, what we have done it, we have just relaxed our threshold a bit. Now if you see from this particular diagram over here, okay, so whenever we relax the threshold a bit, we are picking up more good wines over here, but we are also picking up some bad wines over here as well. Over here we did not pick up any bad wines, right? So this is what happens by using this diagram. We can easily visualize what's going on over there, right? And if you see it over here, the more relaxing the threshold is, we are basically picking up good wines, but as well as we are picking up more bad wines as well. Now if you talk about this particular threshold over here, right, now over here if you see, the classifier is actually not doing any decision making over here. It just picking up everything from this bottle, right? So if you just say in our bag we have good wines and bad wines, right? Now if we just pick up this whole bag, definitely we are picking up all the good wines over here, right? But also we are picking up all the bad wines as well, which is not desirable over here, right? Because when we talk about a machine learning model, it has to identify the good one. Basically here we are talking about a scenario where when we will be purchasing a wine, right, we will be basically looking for a good wines only, right? We will not be buying a bad wines with high expense rate, right? So that's the main motto over here, right? So if you see, by relaxing the thresholds in different, by keeping in different positions, we are basically our picking chance of the good wines is getting higher. Also the bad wine is also getting higher over here. So that's why this machine learning models or classification models comes into picture over here, right? So if you see, like when we talk about machine learning, specifically the supervised learning, we basically do the parameter setup, right? How the model will be performing based on different threshold level, and based on that we will be taking our decisions over here, right? So this is the main concept behind a threshold over there, okay? So we established three things. One is our sensitivity, okay, which is our true positive rate, and we talked about specificity, and we talked about fallout, which is our false positive rate, which is basically our x-axis, and we got a intuition behind the threshold over here. Okay, now let's see, by all of this knowledge, can we just talk about ROC curve over here. Okay, so this is a typical ROC curve look like over here. Okay, so if I just go to our previous slide, so we just established this 4 threshold over here, right? Now for different threshold, what will be our true positive rate value, false positive rate value? If we just plot it, that is becoming our ROC curve over here. So I think we got the intuition over here. So this is our ROC curve, and all this threshold point, if you see, if I just draw it something like this one, we may get ROC curve something like this one over here, where we have a mix and match case over here, right? So we do not have a proper boundary between a good wine and a bad wine. It's all mix up because there are a lot of features are involved over here, right? Now if I just analyze this particular curve over here, so here, as I said, the x-axis is our false positive rate, right? And the y-axis is our true negative rate. That means here y-axis is basically telling me the mode and how you are basically classifying your positive values, and x-axis actually basically telling me how you are misclassifying your negative values over here, right? So if you are classifying more and more positive values, your graph will be higher and higher above. Okay, and if you are misclassifying more and more negative values, it will be going this side and this side above over here. If you see over here, we did not pick up any bad wine over here, so that's why the curve was going up over here. Now the more relaxing our threshold is becoming, the curve is going the right side over here. If you see at the point number 3, it is going more right side over here. Now at the point number 4, where actually we have established the classifier is actually not doing anything over here, it just picking up everything, it is coming in its hand. So here if you see, the curve is actually going more rightward direction over here. Okay, that's the intuition behind this curve. Now it will be more clearer when we talk about the worst case and good case scenario. Okay, so now the ROC curves tells us whether the features we are using to make our decisions are good ones or not. If you see, this is the intuition behind this particular ROC curve, right? Now if I just talk about the best case scenario and worst case scenario of the ROC curve. Now for the best case scenario, what could have happened? Let's say in that case we may have a clear distinction between a good wine and bad wine. Let's say all the features involved to make a wine good or bad, we can clearly say, okay, if this particular feature having this threshold value, which is greater than or less than a particular some threshold value we have, it's a good wine, otherwise it's a bad wine, right? So we have a clear distinction between this one. If you just remember the previous diagram we have seen, there was no clear distinction, right? So this is the best possible scenario we have it over here, right? So here if I just plot our threshold values over here, we can have something like this one, right? So in threshold value 1 we will always get good wine, even in threshold value 2 also we'll always get good wines over here. Now in threshold value 3 we'll always pick up the bad wines over here, right? So if I just draw a curve over here, okay, by applying the same logic what we have discussed in my previous slide, okay, so we may get a curve something like this one. If you see, this will be okay. Let me draw the curve and then we'll see. Now if you see, this is our threshold point 1, right? Now as we are increasing the threshold values over here, still we are picking up all the good wines, because over here we are actually classifying more and more good wines over here. There is no chance that we will be picking up bad wines until and unless we are hitting the threshold value 2 over here. That's why if you see, the curve is going straight up over here till this point of 2 over here, right? Now as we are moving past the threshold value 2 over here, we are actually moving to the bad wine zone, right? That means the more and more wine bottle we will be classifying, all will be becoming bad only, right? So if you see over here, like beyond this particular threshold limit, whatever we are picking up, it is becoming a bad wine, because this is our threshold, right? That is how our data is, something like that one, right? We are talking about a best case scenario over here, right? So that's why the curve is moving sharp right over here. Okay, so this is the, if you understand this particular diagram, the intuition behind this ROC curve will be more intuitive, right? So now let's talk about the worst case scenario over here. In the worst case scenario, we will have, let's say, 50-50% of chance of a particular data point which is either having a good wine or bad wine. That means bad wine, that means like we do not have any kind of distinguishable feature by which we can say this particular wine is good or bad. So this will be our worst case scenario, right? So similar way, if we just place our threshold value over here, if you see in all these places, the value of false positive rate and the true positive rate will be always same, because so there will be a high chance that the negative values will be misclassified as positive, or the positive values will be misclassified as negative, because of this nature of this distribution over here, right? And if you see, like, it doesn't matter where we place our threshold values over here, all the places there will be a chance of 50% of, let's say it is a 50%, it could be 80-20 as well, right? So in those cases, our false positive rate and true positive rate will be almost similar, right? So it will be a graph something like this one, right? So all where here will be our threshold values over here, right? So if you see worst case scenario, the ROC curve will look something like this one over here. The more we go this side, we will be picking up good wines, but we'll be picking up more bad wines as well, right? So that means the more we go up, we'll be shifting towards the right side as well. Okay, now if I just put everything together over here, okay, so we saw the three different cases over here, right? So we are talking about this one is the better one, because here we have a distinguished threshold over here, right? So you can easily distinguish like which one is good wine or bad wine. So the more right side we are going over there till our threshold value 2, we are only picking up the good wines over here. After that, the more right side we are going over here, we are only picking up the bad wines over here, right? Now if I just talk about the area behind these three graphs over here, so in terms of area, this is the best one, the bigger one, right? Then this is the intermediate one, this is the least one over here, right? So area you can easily calculate from here anyhow. Like if you just know integral calculus, then you can definitely know the area under a curve over here, right? Nowadays, like, there are a lot of functions are also available in scikit-learn or in any other tools you use. So even though you do not know about integral calculus, no need to worry about this one. So you will definitely use those functions and get the value over here. But the idea is, like, when we talk about best case scenario, when we talk about worst case scenario over here, the best case scenario is having the bigger area under the curve, right? And the worst case scenario is having the least area under the curve, right? Now the intermediate case is having the value of the area under the curve is intermediate between those two values over here, right? So this is why AOC is important, area under the curve. It basically tells us how good our model is. Basically it's a measurement of our model performance, how it is classifying, right? So if for a different threshold level we are actually achieving the area under the curve better, or more area under the curve, it is basically increasing, we can at least say this model will be performed better compared to the area under the curve, which is little bit lesser from here. So that's the intuition behind the area under the curve, and that's why we use the area under curve as well. Okay, so hopefully, like, those concepts was clear a bit. We were able to understand intuitively why it needed and how it's get calculated. Now apart from those things, there are certain other things as well in confusion matrix which we can use in different scenarios. One of it called miss rate over here. It's basically, if you just remember the sensitivity, our true positive rate, right? So this is 1 minus true positive rate, right? So we basically start with all the good examples over here, okay? then we'll see how we are classifying all the good examples. Now over there we have taken all the good one as a numerator, right? So here we will be taking as all the bad one. In miss rate we will be taking the FN, like the false negative, as our numerator over here. So nothing else. So that's the difference between these two over here. Okay, so if you see, like, this will become our 2/4 over here, right? So now there is another term called precision over here. Now when we talk about precision, we first take a look at the predicted category. Let's say if we are something predicting good, okay, how good it is actually. Okay, so if you see, we have predicted 3 goods over here, right? So among them, the first one is good, second one is we misclassified, and the third one is we classified it correctly, right? So this is called the precision, where now till this point we are actually talking about the actual category, then we have seen how we have predicted it. Now in precision we actually talked about the predicted category and see how it matches with the actual value over here. Okay, so if I just write it down, so here this is our true positive, right? And same by applying the similar logic. So this is our false positive because we predicted something good but it is actually true, not true over here, right? And this is again our true positive over here. So our precision will be becoming something like true positives over all the true positive plus the false positive values over here, which is nothing but our 2/3 over here, right? So precision is basically telling me out of all positive classes, we have predicted all the predicted correctly classes, how many actually are positive. That's the precision over here. Okay, now there is another term called accuracy. Over here we basically judge about overall the data set, right? So how much we predicted correctly, and it should be as high as possible over here, right? So over here if you see, these green ones we basically predicted correctly, and the red ones we basically predicted incorrectly over here, right? So it is becoming the good ones divided by the overall one, right? So we have total 7 data set over here. Among them 4 we have predicted correctly over here, good as good, bad as bad over here. So this is called accuracy over here. Okay, so hopefully this video was helpful. Now in confusion matrix there are a lot of other terms as well, which I have not included here because it will be irrelevant in terms of AUC and ROC curve. Maybe when in future, if it is relevant to our use case, I will be definitely covering them as well. Okay, so hopefully this video was helpful. In next video onwards, we will try to explore all the ensemble learning algorithms. Okay, see you in next video.